Hello, welcome everyone to the Recurrent ETDS seminar. We have had a long waiting time for this visit, but clearly it is worth it because this time we have, to our pleasure, Nachi Avraham, who will be telling us about L2 cohomology of amenable groups and a difference between left and right. Over to you, Nachi.
Hey, thank you, Nishant and Shilpak, for the invitation. So what I'm going to talk is joint work with Zemer Kosloff, um, and it's going to be. I'm going to split the talk into two parts. The first part will be more group theoretic, potential theoretic representation and stuff, and the second talk will be much more connected to ergodic theory and more dynamics aspects of this of the first part. So let me start. The talk will be more or less five parts, and let me start with the first part. Will be about some basics, general objects and definitions, and the basic question that I'll suggest. So let G be a countable group. We typically assume it's infinite. That's always be the case in this talk. That's what G stands for. And whenever we have such a group, we can consider the action of G on the vector space R to the G, which is given by translating the argument of the function from the left. Okay, so um, I will denote this action by lambda. Okay, so every function f can be translated this way from the left and get a new function, and this defines an action of G on this vector space R to the G. Now, the left regular representation of G, which I will also abbreviate by lambda, is a restriction of this action to the subspace of R to the G, which is just L2. Those functions from G to R, which are square summable. Okay, so when we look at the norm of this space, then of course this action can be seen to preserve the norm. It's a unitary representation, and this is the so-called left regular representation. Now, next, let me present another object, algebraic object of the group, defined for the group. So we have the notion of cocycle for lambda. We have a more general notion of cocycle for representation, but here I will specialize to cocycle for the left regular representation, lambda, which in this talk, I will refer by cocycle to a function in R to the G, some function from G to R, such that the difference, if I translate this function from the left by some element G in G, and I compare it to the original function, then this difference is a function of L2, square summable. Okay, so f itself is not square summable potentially, but somehow the translation of f by some element G compared to the original function f, this difference is square summable. Now, let me just say something about the terminology. So when people, the standard terminology says that the cocycle is not the function f, but the map that BF, which is a map from G to the L2 of G, which is given by this difference. For every group element G gives us an L2 element by looking at lambda GF, the translation of f from the left, minus f. So this is called cocycle because it satisfies the cocycle identity, okay, which is written here, but let us just forget about all these fancy names and words. We're really interested in function, and I will abbreviate this I'll just, call it for the sake of this talk. It will be convenient and natural to call the function itself cocycle. So a cocycle for lambda for us will be a function f, so with the property that lambda gf minus f is square summable. Now we have trivial cocycle. So in case the function, so we have two sources of triviality. The first is L2 of G. In case the function f itself is square summable, then of course translating it as square summable taking the difference of two square summable function is square summable, it's obviously a cocycle. And also, if f is constant, then of course translating it and looking at the original function just gives a zero function. And because it is vector space, of course, we can sum these type of trivial cocycles. So we get the space of coboundaries as the space of L2 plus R. So all functions which are square summable potentially plus a constant. So these are considered as trivial cocycles. Okay, they're called coboundaries. Okay, so any question about these definitions and okay. So now we have the notion of cocycle, so we
Okay,
can consider the
probably you're going to get to it, but just on Z, is there a very obvious non-trivial cocycle, sorry, non-coboundary cocycle that you can sort of describe?
so it's a good question, but yes, I mean yes, it's not so easy to construct those. It's kind of they call it L2 cohomology theory, and it's a rich theory, but it's not so easy to come up with a non-trivial cocycle. But in the case of Z, it's not hard. I mean you can it's just you can yeah you can consider a function which just goes back and forth in certain way, so the differences are very small, but it doesn't converge itself or to a constant. So it's not that obvious, but in fact, even to know that on general group you have such a thing, it's not so obvious how to construct such a thing. But I will get to that. Some aspect of this question will appear later on.
Okay.
So let us consider now the space of cocycle. So I'll call it the left, because of the left regular representation, L2 Dirichlet space of G. So it's the linear space of all function in R to the G, which satisfy what I asked before, which the difference between the original function and the function translated from the left by some group element is in L2. Okay, so I denote it by D2 of G with respect to lambda. And this is a vector space, okay? It's some subspace of L2, sorry, it's a subspace of R to the G, okay? Um, so far I took the convention, the left convention, okay? But of course, one can consider everything analogously from the right, so we can take a rho to be the action of G on R to the G from the right, okay? So again, if I have a group element G and I have f, which is a function from G to R, I can translate the argument of the function from the right, okay? And I get an action. Now, all objects I mentioned before can be defined in an analogous way. So we have the right regular representation, which is just the restriction of rho to the L2 space. This is also a unitary representation. We have cocycles for rho, okay? Just function which right translation compared to the original function are square summable. And okay, we can define the Dirichlet space uh, corresponding to the right regular representation. Um, okay, so let me make the observation that in an abstract way, the left and right regular representations are unitarily equivalent. What does it mean? In other words, or one aspect of this is that the left and right Dirichlet space are isomorphic in a natural way. If one have a cocycle for lambda, for the left regular representation, say f, then if I change the variable in f, doing inversion of the variable, then I get, of course, a cocycle for the right regular representation. Okay, that's just direct verification. So in an algebraic sense, in an abstract sense, those vector spaces are just obtained as inversion of the variable and this kind of natural isomorphism between them. They come naturally isomorphic. But as a subspace of the ambient space R to the G, no one guarantees that they are the same. Okay, if I look at a specific function in R to the G and I ask myself, is it in the left Dirichlet space? Is it in the right Dirichlet space? The answer might be different between the two. Okay, so I would say algebraically as abstract vector spaces, it's fine. They're all the same. It's just take the convention from left or from the right, work with whatever your favorite convention. But when you look at the geometry of the group itself, how translation of element in the group behave, then who says that they are the same? Maybe translation from the left behave different from translation from the right. Okay? And that's the main question I want to study. And soon I will formulate it more precisely. Let me just say some new terminology. So let me call the element which are both cocycle for the left and for the right symmetric cocycle. Okay? Either I translate them from the left, either I translate them from the right, comparing them with the original function is cross-summable. And the element which lie only in one of these spaces, maybe in the left but not in the right, or in the right but not in the left, I call them asymmetric cocycle. Okay, maybe they do not exist or exist. Okay, we're going to discuss that, but just terminology-wise, let us use this convenient terminology. And let us make the observation that coboundaries, meaning those function, L2 function or constants or sum of such, are always symmetric. Okay, both obviously satisfies the two directions, two-sided cocycles. I mean, they both translate them from the left, comparing to the original one, translate them from the right, comparing to the original one, they will be square summable. So every group always have symmetric cocycle in trivial way, but okay, but what else? So let me suggest the first question. When does a group admit an asymmetric cocycle? Okay, maybe we can observe that, okay, abelian group, of course, do not have asymmetric cocycle. This it's literally the same to translate from the left or from the right. But okay, beyond the abelian group, what groups can have an asymmetric cocycle? Some kind of strange function. Okay, if we forget all the fancy terminology, it's a very concrete question. Okay, we have a general group, non-abelian, okay, otherwise it's trivial. And I ask you, can you construct a function on this group? So if I translate this function from the left, the difference from the original one will be square summable by any group element I like, but not so from the right. But if I translate this function from the right and compare it to the original function, maybe this will no longer be square summable. It's kind of different geometry between the left and the right action of G. Okay, that's the basic question I want to study. And I'm going to get to that only in the second part of the talk, but I will just mention that our motivation came from the ergodic theory of the non-singular Bernoulli shift model. Okay? And I will explain why this is the key, why this is the property that is relevant to that. Okay. Any questions?
What is non-singular Bernoulli shift?
I will get to that. Sorry, that was just a short title.
Okay.
I didn't say anything about that, but sure, I will get to that. Oh, I'm sorry. I'm going to stop sharing for a moment because I think I have the wrong version of the presentation. Sorry. There's one slide that is missing. Sorry for that.
So while we are waiting, I should know this, but perhaps I don't. For Z, do you so you mentioned that there are non-trivial cocycles always for all infinite amenable groups?
Yes. Yes. Sorry for the
No worries.
sorry for the delay.
Actually, we could have paused recording, but
Okay. Let me now share my screen again. Um, okay, so this is the main question I want to present, and now let's dive into some answers to this question. So let me just, for the sake of general context, recall briefly what an amenable group is. So we have a group G, we call it amenable if for every finite set K in the group G and epsilon and positive epsilon, there is some finite set F in the group G, so that the boundary of F compared to F itself, boundary of translated by G, is small, okay, than epsilon for every G in K. Okay, so this is one of many ways to define amenability. Okay, okay, it says that if I take any finite set K and I can find some other set F, so the translation of F by some element from this original set K would satisfy this smallness condition. So if I look at the difference between F before and after I translate it by G compared to the original size of F, this is smaller than epsilon. Okay, so this is, okay, I guess most of you saw that once, but let's just take it as an abstract definition. I'll give you just some examples. Okay, so for example, ZD may be the most classical example of amenable group, but in fact, there are many other examples of amenable group, like okay, abelian groups more generally, or even more generally solvable group, or groups with like sub-exponential growth. There are many other also examples, but the basic non-example of amenable group is three groups, okay, for rank more than at least two. And other examples of non-amenable groups are infinite group with property T, for example, SL3Z is such an example. And okay, we don't really need to get into those examples in details. I just mentioned that briefly for the context, but the most important thing I want to mention is that this type of way to define a amenable group, because this will play a role later on, but so that's the only thing I really wanted to say about amenable groups. Okay, so it's just a short reminder. And here is another theorem that I will. Here is the first theorem I want to say. I want to present without talking about the proof. Is that we have kind of striking phenomena in non-amenable groups with regard to the previous question. So we ask when does a group admit an asymmetric cocycle? So in case the group G is non-amenable, for example, the free group, then something interesting happened, which in fact I would say something not completely correct, but soon I will retract that. By every cocycle, unless it's trivial, every cocycle is never symmetric. Okay, meaning the following: if you have a cocycle which is both for the left regular representation and for the right regular representation, then it must be the trivial cocycle. Okay, if you take kind of generic cocycle, or sorry, if you take some cocycle which is non-trivial on the group, then it must be either, say, for the left regular representation, that it will never be also cocycle for the right regular representation. Okay? That's an interesting phenomenon in non-amenable group. And I want to now to make a reservation for what I said before. In non-amenable group, for example, in the free groups, there are many cocycles which are non-trivial. But there can be non-amenable group which do not have any non-trivial cocycle. So this is a result of property T, which has more than that, but in particular, we're specialized to the left regular representation. It just said that every cocycle is trivial. So this does not mean that every non-amenable group has an asymmetric cocycle. It does mean that the symmetric cocycle are just trivial ones. And with regard to other non-trivial cocycle, well, it's a whole world of, it's related to Betti numbers of groups. It's a whole story. Okay. So I want to rephrase the question now, just for amenable groups. Okay. Sorry, maybe just some credit. So one direction this theorem is by Stefan Vaz. He communicated this to us a few years ago. He didn't publish it, and we included it in our paper with his permission. and the other implication is ours. So this maybe answer what you mentioned before, Nishant, that for example it says that if G is a amenable group, okay, then you will always have kind of even you will always have a cocycle which is non-trivial, okay? Because if G is amenable, then this intersection does not equal to the trivial cocycle. I mean, you can find some non-trivial cocycle, which is in fact for both the left and right regular representation simultaneously. Okay, so I'm now rephrasing the questions. So we have an amenable group G, and I want to ask, does it have an asymmetrical cycle? Can on an amenable group, one can construct cocycle, which is for the left regular representation, which is not for the right regular representation. A function which is square summable if I compare it to the left translation, but not so compare it to the right translation. Okay, so this is kind of general background, and now I want to get into our main result, which gives characterization that answers these questions. Okay, any questions so far? Okay. So let me start with kind of a basic obstruction to find an asymmetrical cycle. Okay, and this is called the property, it's an algebraic property of group, which is called FC group, finite conjugacy class. So a group G says to have to be an FC group if the conjugacy class of every element is finite. Okay, every element in the group G has finite conjugacy class. Okay, so this is of course a billion group, for example, our FC group. Okay, but there are other groups which are FC groups, and let us make the observation that FC group cannot have asymmetrical cycle. Okay, so if G is a billion, or more generally an FC group, then every cocycle for the left regular representation is automatically also cocycle for the right regular representation. Why is that? It's a basic exercise. I will review it very briefly here. And so one can say that we can kind of move from the right regular representation to the left regular representation by paying with some conjugate of the element. Okay, the price to move from one to another is by inserting conjugate of some of the elements G and H. Now, if I have now a function which is a cocycle for the left regular representation, then it also cocycle for the for the right regular representation, because when doing this, when looking at this L2 norm, then it is bounded by all possible conjugate that the element G has, which is just finitely many of them, and then some L2 norm which relate to the left regular representation. Okay, it's a basic calculation. There's nothing really deep here, but this is a very simple bound, and which is finite because f was assumed to be a cocycle for lambda. Okay, so and then symmetric arguments show that also the opposite inclusion holds. So this is I would consider it, this is really the basic obstruction. I mean, when you look at a billion group and you look, okay, can it generalize a little bit? Then finite conjugacy class of every element is the basic obstruction to have an asymmetrical cycle. Okay, one can routinely prove that for FC group, every cocycle for the left regular representation is also cocycle for the right, and vice versa. So this is not possible. On FC group, you would never find an asymmetrical cycle.
So just a very basic question. If I have a subgroup which is an FC group, does this already imply? No.
This is an algebraic property, just
right. Okay, sorry.
Sure. Okay, so here is our first main theorem that, okay, it says that in fact this is the only obstruction. Okay? Sorry, among amenable groups, this is the only obstruction. Okay, so if G is an FC group, then of course, as I just told you, then every cocycle for one is also cocycle for the others, but in fact, the opposite is also true. If G is not an FC group, if it admits one element which has an infinite conjugacy class, then we can guarantee you can find an asymmetric cocycle. You can find a function with this funny summability property, one-sided summability property. Okay, so I'm not going to present the proof, but I do want to say something about what geometric property of the group explains this phenomena. Okay, because it really says something I would consider surprising, okay, to me at least, that there is a function on the group which, if you translate it from the left by any element, it's square summable, compared the difference with respect to the original function, but not so from the right. I think it reflects some geometric property of the group that we can capture. In the amenable case, we can capture it, I think, with the following, with something that I'm going to present to you. So let me make a definition. So let G be a amenable group and assume it is not an FC group. It means that there is some element, call it S, which has infinite conjugacy class. So a left scheme, or S left scheme, is a sequence of finite subsets of G with the following properties. So there's going to be a competition between what happened when I translate these sets from the right and when I translate these sets from the left. So when I translate this set from the right by the element S, by this special element S, the disjointment is full. Okay, those just do not. Every set, if I translate it by S, I just outside this set for every n. On the other hand, if I translate by now, I ask for every group element G in G, if I translate this set by G from the left, then it's kind of small. In what, not only small, but summably small. What does it mean? So I look at and compare En before and after I translate it by G, compare it to the original size of En, and I get that over N, all those extra elements that I got is summable. Okay? So if for example, comparing this, if for example, translating En from the left would be disjoint from En. So the set GEN and En would be disjoint. So this size would be just 2 times En. Divided by n, it would be just infinite sums of 2, okay, which is infinite. But so this smallness condition says that, okay, while translating by the element S from the right somehow give us very much disjoint sets, when translating it from the left, we do not have this property. We have kind of more and more overlaps. Okay, so this is just terminology, make a definition. And now the main observation is that left schemes, this sequence of sets En exists if and only if G is amenable and non-FC group. I will just mention without defining exactly, but this second property is just kind of reformulation of the Fellner condition for amenability. One can show that it is in fact equivalent. To get also the disjointness, in the first part, one needs to play with one element which has infinite conjugacy class to get that, okay? If a group is an FC group, then you will never be able to have these two properties at the same time. Now, with this notion in hand, we can cook up. Sorry, yes?
Sorry, can I, in Z, just if we take the group Z and take En to be minus n to n, then I guess the sum you will get is 1 by n type, right? Like you take G to be, let's say, plus 1, then
Okay.
the difference is just the difference in cardinality is 1 in the numerator. So this will be like sum over 1 upon 2n.
Right, but the
So
first
which is
condition won't be satisfied.
okay. I see. Okay.
Okay, because if the group is a billion, then En, if you translate En by S from the right or from the left, is just the same.
Yeah.
Okay?
Mm.
And Yeah, so do note that maybe it's written in kind of confusing way because in the second property I want it to hold for every G in G, and the first property just holds for this unique element S.
Oh,
Okay, but
oh.
okay, so if we have a left scheme, if certain group has a left scheme, and I told you that okay, if group is not an FC group, then it doesn't have a left scheme. But let's just forget about this property. Suppose a group has a left scheme, then there's some kind of okay, we need to do some further combinatorial massage to the set En to get some kind of extra disjointness, but after we do that, we can define a function of this form. We can define a function that measures in how many sets the element H lies, divided by square root of the size of En, and I get this. This would be finite valued, okay, function. And the disjointness condition, the first condition gives us that if you translate it from the right by S, then you just get kind of infinite disjoint copies of something, and you get infinite. Okay, comparing it for the original function, this difference is just sum of two. It's kind of infinite sum of twos. But so F is not a cocycle for the right regular representation. But the boundary resummability, the second condition, is translate into the condition that F is, because the L2 norm of F minus lambda GF can be bounded by this infinite sum, by this infinite sum, which is finite valued, okay, which converges. So I'm not, there's some kind of algebra to do here, which is quite annoying, but I think the way to look at this phenomena is by looking at this, the notion of left scheme. This, I think, the existence of this scheme is, I think, tells us something about the Feller geometry of the group. It says that you can find some kind of Feller sequence which behaves very different from the left and from the right. That's what one needs to cook up an asymmetrical cycle. Okay, questions about that? Yeah.
Sorry, Naki. Is there a very simple case where you can tell me what the left scheme looks like? For example, say the infinite dihedral group. Is there something like intervals or like? Do you have like a very quick?
Yeah. So great questions. Great question. You see, the last section is the Heisenberg group, and if I have time, I can show a very concrete construction of this left scheme for the Heisenberg. Okay. So let me now get into dynamical aspects of this phenomenon. Why all this? This sounds like group theory, maybe geometric group theory. Why is this related to dynamics or ergodic theory? So let me present the model of non-singular Bernoulli shift. Okay. So let me start by what is a non-singular action. Okay, so it's kind of generalization of measure preserving action. So we have a group G, and we have a probability space X, mu, and by saying that G acts in a non-singular way on this space, I say that, okay, G acts in a measurable way on the Borel space X, just measurable action. And the measure, okay, maybe it preserves under the action of G, measure preserving, but it may not be preserved, but maybe the measure class of mu is preserved under the action of G, which means that if I push forward the measure mu by some group element G, I get a new measure, maybe not the original measure, but it is absolutely continuous with respect to the original measure. Okay, so this is also called quasi-invariant action or measure class preserving action. It has other names, but let's stick to the name non-singular action. This is a general notion. Now, let me also suggest a model, the so-called Bernoulli scheme, which again, like in the non-singular, we have the classical setup of probability preserving action. This is kind of generalization of it. Also in the Bernoulli scheme, I'm sure you all know about the classical Bernoulli scheme, just, coin toss, fair coin toss, but here is kind of non-singular analog of this. So a Bernoulli scheme on a group G is a probability space of the following form. So I'll denote it by omega sub G. This is just the space of 0, 1 indexed by G. And I have a product measure on this space, which is just, I'm fixing some function, some probability. So it's a function between zero that takes value between 0 and 1. And I look at the product measure, which gives, say, 0, the probability f of h, and 1, the probability 1 minus f of h. So if f is constant, let's say fh is constant and equal 1/2, then we get the classical Bernoulli shift, right? Or f is constant and equals p for some p between 0 and 1. Of course, we got just the product measure p1 minus p. But here we allow f to vary with the coordinate. Okay, so it's independent coordinates, but not necessarily identically distributed. Okay, so this is for me what a Bernoulli scheme on the group G. Okay, so now let me try to connect these two notions. So first, a Bernoulli scheme has a very natural action by translating just the shift action. Okay, so let's consider call it by L, the left shift. So G acts on omega G. If I take a configuration of 0 and 1s indexed by H, then I can just translate it from the left. Okay, that's the shift action. And if we are in the case of classical Bernoulli shift, when it's IID sequence, all coordinates are identically distributed, then of course, if I translate the measure from the left, from the right, it doesn't matter, then I get the same measure, okay? It's the same configuration of IID run the variable before and after I translate it. So of course, the left shift action preserves the measure. Okay, so it becomes a probability preserving action. But more generally, I ask for which function f that gives me the marginal distribution, and now I allow the marginals to vary, when does the left shift of the group G on the Bernoulli shift is non-singular? When does the measure class of this product measure is preserved under the left action? So this is kind of maybe a too complicated setup. Please ask if there is anything that it was not completely clear about the terminology or setup I mentioned. Okay, so we have classical Bernoulli shift, just probability preserving. I translate an IID sequence, I get another IID sequence with the same distribution, no problem, it's probability preserving. But now I get an independent sequence, but not identically distributed, and I translate it. I still get, okay, independent random variables, but no longer with the same marginals. Can the product measure before and after the shift be absolutely continuous? So the action, this left shift action, is non-singular. That's the basic question. So we can study this system dynamically, okay, as a non-singular action of the group G. So this has a very striking answer by Kakutani, classical theorem of Kakutani. It says there is a very clear kind of quantitative condition for that. So in order that f is kind of, okay, parameter of this measure, so the left shift is non-singular if and only if the square root of f and the square root of 1 minus f both lie in the left L2 Dirichlet space. So I look at the function square root of f, and I ask myself if I translate it from the left and compare it to the original square root of f, is this different lie in the L2 of G? Is this an L2 function on the G, on the group G? Okay? In other words, if I have kind of configuration of marginal distribution on the group, I ask myself, okay, take the square root of those marginal distribution and translate them from the left. Now look at the difference. All differences between before and after you did this shift. Is this square summable? If yes, and only if, Kakutani says, then yes, the measure class is preserved under the shift. Okay, this is a particular case of Kakutani theorem is more general about general product measure. It's not about this dynamical way of putting it, but this is just direct consequence of his theorem. And so and this needs to be held for these two functions, square root of f and square root of 1 minus f. Because of the square root is not automatic. It's not the same. You need both. But
So
sorry?
if you have an amenable group which is non-FC, but you needed both for square root of f and square root of 1 minus f.
Yes.
So your construction does not immediately give you something which is non-singular with
Sorry.
respect to the left action, but maybe singular with
Yes.
respect to the right action.
So
That
the
is not
answer is
immediate.
yes. The answer is yes. Our construction does give we can construct such a function f
Okay.
whose square root and the square root of 1 minus satisfy that it is in the left Dirichlet space, but not in the right Dirichlet space. So we can get a non-singular from the left, but not from the right. That's kind of immediate consequences. But I want to take this further into more dynamical results, not only about whether it is non-singular or not. Okay, so I'll explain that right away. So okay, so this is the model of non-singular Bernoulli shift. Okay, we have a Bernoulli scheme, which is kind of just general probability space for the group G, just 0 and 1 indexed by G. We have a class of product measures on it. Okay, take any marginals, any configuration of marginals we want, and we have the Kakutani criterion that tells us when it is non-singular for the left shift. And analogously, one can formulate this criterion for the right shift. Okay. Now, our motivation was to construct left non-singular but not right non-singular. And this does give us, but I want to construct more than that. And because this is not really still dynamics, I argue, but we need some more kind of recurrence properties or mixing properties, so it will be really meaningful from dynamical point of view. Let me explain what I mean. So what is the notion of conservative non-singular action? So generally speaking, a measurable action, non-singular action is conservative if it is recurrent in a measurable sense. Okay, so it is not maybe defined pointwise. We need to consider, almost sure behavior, but in a measurable sense, it needs to be recurrent. In the probability measure preserving case, this is always true. This is just a Poincare recurrent theorem. Whenever the group is infinite, then and acts in a probability preserving way, we will always have conservativity, okay, Poincare recurrence. So soon I will define this more properly just for background. And for general non-singular actions, conservativity is challenging. I mean, it's often a hard property to verify, and it's often the most delicate of the ergodic properties to verify for non-singular actions. So let me define it more properly. So suppose we have a non-singular action of some countable group G on some probability space, and it is conservative if it satisfies Poincare recurrence. So what does it mean? For every measurable set A of positive measure, there is some non-trivial group element such that the measure of G of A intersection with A is positive. Kind of the set A returns to itself using some non-trivial element. There are 100 others way to put this property, but this is maybe the most intuitive one, the Poincare recurrence. And here is another way to put it, which is kind of standard. I won't talk about why it is equivalent, but it's standard fact in the literature. So this property is equivalent to that property. And what does this property say? So remember that what is a non-singular property mean? It means that if I push forward the measure mu by G, I get something that is absolutely continuous with respect to the original measure mu. This means that I can take the random-Nikodym derivative of those measure for every G. For every element G in G, I can look at this random-Nikodym derivative. Then conservativity means that if I sum all of those random-Nikodym derivative at any point, at almost every point, then I get infinite sum. Okay, this is just another way to define conservativity in the non-singular setup. Just as a sanity check, in case we are probability preserving, these random-Nikodym derivatives are all just 1. Okay, G push forward of mu by G is the same as mu. So this random-Nikodym derivative is 1. This is just infinite sum of 1s, and this is infinite. Okay, but this is the general notion of conservativity. There is many other ways to put it. It's a delicate property and much less innocent than in the probability preserving case, and it's something challenging to show in general. Okay.
So is your
Now,
skin property just
sorry,
saying that a point visits positive
you
measures
can,
infinitely many times?
yes,
That's kind of
yes.
what
There
you're
is
saying.
also a pointwise recurrence version of this. Yes. You can say that for every point A and mu almost every point in this subset, you can find, and you can also say that there are infinitely many elements G and G that satisfies this, and infinitely many elements G satisfies the pointwise recurrence. There's too many ways to put it. Yes, I just picked two. Yeah. Okay, so I wanted now to say something about conservativity of Bernoulli, of non-singular Bernoulli shift, which is also, this is one of the cases where it's very delicate to verify whether a non-singular Bernoulli shift is conservative. Before that, let me just mention a terminology. So let me say that a Bernoulli scheme satisfies a doubling condition if the marginals just stay away from 0 and 1. Okay, so I have some, okay, say Bernoulli scheme whose marginal distribution is f of h, yes, given by some function f, then I want this function not to tend to 0 or to 1, just to stay away, say, between 1/3 and 2/3. Okay, let's call it doubling condition. Now, here is an important criterion for conservativity of Bernoulli shifts, of non-singular Bernoulli shift, due to Evas and Val. It's about, a few years ago, and it's very useful. It gives something about the growth of the cocycle, which is translated to conservativity. Okay, more concretely, suppose we are given a non-singular Bernoulli shift, so we have the left shift action of G on some Bernoulli shift with some function f, and I assume it is non-singular, meaning by Kaputani criterion that f satisfies that the square root of f is in the Dirichlet space, and the square root of 1 minus f is also in the Dirichlet space. Now, I assume also that it satisfies the doubling condition, okay, that I mentioned just before. And now, here is a condition that guarantees conservativity. So you have some sufficiently large constant kappa so remember that, okay, f is the function that gives us the marginal distribution of the Bernoulli shift. Being non-singular means that this is in L2, okay? I know I said square root, and now there's no square root, but because of the doubling condition, it doesn't matter, okay? As long as functions stay away from 0, it doesn't matter if it has square root or not, so forgive me about that. Now, okay, I need to multiply by some big constant. It's allowed, okay? And I want the exponent of this to diverge. So let's imagine the case that is probability preserving. What does it look like? Probability preserving means that f is a constant function. This means that translating f and comparing it to the original one is just 0. So the exponent of 0 is just 1. Infinite sum of 1s is infinite. Okay, so probability preserving Bernoulli shift, yes. Concurrent recurrent tells us it is conservative. But as long as this cocycle doesn't grow too fast to pull this exponent very fast down, so this diverges, as long as this has not happened, the Bernoulli shift will be conservative. Now, I don't want to get into this as why it's true. I just want to mention that this is the tool that inspired us for the following construction. So I want now, sorry. So I want now to tell you that, okay, I wanted to construct a non-singular Bernoulli shift which is left non-singular, sorry, a Bernoulli scheme which is left non-singular but not right non-singular. But I do want to do it in a meaningful way. I do want to construct it so it is conservative. Right? So it kind of demonstrates dynamically meaning behavior. Okay, that's one can think of conservativity this way. So I can use this criterion to go back to the left scheme definition that I said and try to cook up a left scheme which satisfies this extra recurrence condition. So let me now put it more precisely. I'm going to skip this just for a second. And I want to refine the notion of left scheme by incorporating this recurrence condition. So suppose we have an amenable group G, and suppose it is not FC. Not every element has finite conjugacy class. So we fix such an element S. And I want to define the notion of recurrent S left scheme. So it's a sequence of finite subset. As before, I want these two conditions, which is just the basic definition of left scheme that I mentioned before. Now I want the extra condition, which is inspired by this condition of VAS and val. So there is some constant kappa, so that this infinite sum diverges. Now, okay, I didn't say algebraically how does this relate to the Bernoulli shift and the cocycle, but now you can see the connection, okay? When you cook up Bernoulli shift out of this, you can bound those series by one by another, they are comparable, and you can cook up such a Bernoulli scheme that satisfies this condition in VAS and val, so it is conservative. Now, let me go back. I'm sorry that the order here was a bit messed, but the result of this refinement of the notion of left scheme is that every amenable group which is not an FC group admits a Bernoulli scheme with the following kind of funny properties. On one hand, the left shift is very good, demonstrates very good dynamics. I mean, left shift is non-singular and conservative. It demonstrates recurrence. But the right shift is the furthest one can have. It's just meaningless from dynamical point of view. Okay? Moreover, just by applying previous result of Kosloff and Danilenko, once you have a Bernoulli, this Bernoulli shift can be shown to be, in fact, weakly mixing. So we can construct kind of configuration of marginal distribution on the group. So if I translate them from the left, I get something very interesting from dynamical point of view. It's non-singular, it's conservative, it's weakly mixing. I mean, it's a super legit system to study with lots of dynamical properties to look at. But if I translate it from the right, kind of this coin toss that I translate it from the left, I get lots of interesting dynamics, but translate it from the right, I get something completely different. Something that statistically is just nothing like the original system. Okay, that's the meaning of this construction. Now, we indeed show that strengthening of the previous result that, yes, this is indeed possible in every amenable group which is not an FC group. If the group is FC, this is never possible. It's like the abelian case, left and right essentially are the same from this point of view. But as long as the group is not an FC group, then we can get this kind of asymmetry between the left and right behavior of the group. Now, okay, let me, I have one more. I'm not sure how much time I have left. The last question is really concrete construction on the Heisenberg group, which I can do soon, but maybe time for general questions. Maybe Nishan to let me know where are we in the,
So
how
we
long?
have 5 to 7 minutes. We have 7 minutes. But yeah, as you wish, we can wait for those. We can have some questions and then we can go on to the.
Sure, I think no, that should be enough. Yeah.
Okay.
So sorry. So any questions about what I mentioned so far? Or? Okay. So let me show you, take the Heisenberg group. Okay. I mean, that's the first example actually considered, because this is, it's kind of very close to be a abelian group in a sense. And we wonder, does it have left non-singular Bernoulli shift, which is not right non-singular Bernoulli shift? Okay, that's Zemer asked me this question, I don't know, a few years ago during my PhD, and we couldn't solve it back then, even for the Heisenberg group. This is kind of, I would say, the first example that comes to mind. Okay, and let's see why the Heisenberg group does demonstrate this kind of asymmetry between left and right. How to see it using left scheme. Okay, and it's going to be concrete. So consider the Heisenberg group with this presentation. Okay, so it's generated by xy. Z is the commutator of y and x. I'm taking this convention of commutators. And Z is the center. Okay, it commutes with x, it commutes with y. And this is a presentation of the classical Heisenberg. Now I want to construct a left scheme, kind of sequence of finite subsets. When translated from the left by some element, they behave well, they kind of small. By translating them from the right by some special element gives very disjoint behavior, very much non-Fellner behavior. Okay, so let's start by choosing sequence of integers a and b and c, and with some ability properties. Okay, just I engineered these properties because the quantities we get later, but let's take them as parameters of this construction. Now I have this a and b and cn, and okay, I choose also now a sequence of small bn's, which grows fast, so some other disjointness properties hold. Okay, I look at those big bn, and okay, I just take very fast sequence of integers bn, so that both it's larger than cn and satisfy this property. Okay, it's some kind of no need to think too much about these properties. It's just again engineered to satisfy the property that we're going to see. So we took as input a and b and cn, okay, capitals. I define some extra sequence of integers, call it small bn, and now I want to define the sets in the Heisenberg group that will demonstrate this asymmetry between left and right. So the definition is the following. So a general element in the Heisenberg group can be presented as x, y, z with some powers, some integer powers a, b, and c. I want to limit, at the level n, I want to limit the power a of x to be between 0 and a. I want to limit the power b of y to be between bn and bn plus capital Bn. And I want to limit the power of c, the power of z, c, to be between 0 and cn. Okay? It's kind of boxes, parameter, it's just boxes in the Heisenberg group, parameterized by those integers that I didn't yet specify any property of them. And I claim that this is an so-called X left scheme. X is indeed an element with infinite conjugacy class, okay, in the Heisenberg group. Let's see why it behaves differently from right and left, this type of boxes in the Heisenberg group. So if I multiply a general element is given by x to the power of a, y to the power of b, z to the power of c, and I multiply it from the right, then what happened? So I need to pay twice with the commutators, and I get this presentation. So it adds 1 to a, and it adds b to the third coordinate. Okay, this is just the presentation of the Heisenberg group. This is the relation that's written there. Okay. Now, as you can see, by the choice of the parameters, if b is larger than bn, as I required before, if the element x to the a, y to the b, z to the c belongs to the en, to the set en, then b must be larger than bn. That's by condition. So b plus c is greater than cn. So this gives that the last element goes outside the cn coordinate. So this kind of very simply algebraic condition that tells us that you have disjointness when multiplied from the right. Okay. However, the very same set multiplied from the left have much more overlap. Why? So let's see, for example, multiplication by x, that's the simplest one. You just add 1, right? When I multiply an element xa, yb, zc by x from the left, then you just add 1 to the power of a. This is kind of negligible, okay? It doesn't add much to the boxes. Okay, and you have this, okay, you have kind of this approximation, okay? Similarly, if I multiply it by y, it adds nothing to the power of a, it adds 1 to the power of b, and it adds a to the power of c, okay? Which is still fine. I can control those powers and get, again, computation, but it is controlled in terms of sum. The infinite sum converges. So those boxes, because of the nature of the multiplication Heisenberg group, show that right multiplication behaves different from left multiplication. Now, I'm not going to say much about it, but you can even make it recurrent with some extra condition. If an grows sufficiently large, and you get some approximation that tells us even recurrent left scheme, but I won't get into that. So in many concrete cases, also in the paper, we included some concrete examples. In the Hadler group, in other groups, you can actually see those left schemes, those sequence of finite subsets which demonstrate different left and right behavior. Okay, so this is the geometric property I think that explains best this asymmetry. Okay, thank you very much for listening.
Let's thank the speaker. I open the floor for questions. So I have a question, which is somewhat tangentially related to whatever you said, and maybe the answer is easy. So here you're differentiating between, singularity and non-singularity of the left and right actions in some sense, right? And that is being given by FC groups. Now, in non-singular theory, maybe this does not make so much sense, but still I'll ask. What about isomorphism? Suppose we are an FC group, and suppose I have a non-singular scheme. Is it obvious, or is it even true that the left action is? And suppose we are dealing with a non-singular conservative Bernoulli scheme. So now you know that if it's left, then it's also right for the same things. But are they isomorphic systems?
So if you take the isomorphism, like a TT inverse I don't know where.
I'm not
So um
although now that I think of it, I kind of okay. So there are two variants of the question, right? One is right. So uh, I guess it doesn't make sense to talk about isomorphism of a left action and a right action in that sense. But maybe
no, it's not left action and right action, but both
yeah,
action
exactly.
are kind of
Multiplication
so
on the
it
left and
does,
multiplication on the right. Yeah,
yeah.
yeah, yeah.
So I think it does make sense, but I really don't think I can say anything about that from the topics from what I considered here.
Yeah,
But it's a very interesting. I mean, I have no clue. It's really, really, I didn't think about that. Um,
even for okay, so even for Z, if you take the left shift and the right shift, I know shifts of
yeah.
finite type for which left shifts and right shifts are not isomorphic, could not conjugate to each other.
Yeah,
But
but it's like the shift and the inverse of shift.
yes, yes,
Are the shift isomorphic to one another? I don't know. It's a great question, and I actually don't think that the fact that say both are non-singular or both are conservative or any kind of this really gives you this I can give you some sort of isomorphism. It's kind of that's my feeling. It's a different question, but I
so I'm
really
guessing
don't know.
that towards the left, if your the function f behaves very differently from how it is on the right, I guess maybe yeah, okay. I have no idea either. Just something
Yeah.
which came to my mind while listening to you.
Um,
What about non-amenable? So non-amenable groups. So this result by Vas and I don't remember was telling us that if you're non-amenable, then there are asymmetric cocycles.
Not always. Depend if it has positive
Ah, right, right,
L2 Betty
right,
numbers or
right,
not.
right, 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 right. Right.
But as long as it has positive Betty number,
Mhm.
then take any non-trivial cocycle for the left regular representation, and you know automatically that is not a cocycle for the right regular representation,
Mhm.
just by non-amenability.
I see. Oh, very interesting talk. Anyways, other questions, other thoughts. Okay, I guess that is that. Let's thank the speaker again.
Thank you very much.
Recording.